Hello everyone and welcome to BoostBusters Gas Exchange Handbook. And today we have reached chapter 80. This course should be dealing by four-stroke engines and charging systems. So when does it become interesting with charging systems? Well, where we want the brake mean effective pressure on the four-stroke engine to come close to 20, or delivery ratios well beyond 1, then it's time to consider a charging system where the air density can be increased by boost pressure. A charging device can be a supercharger, which is defined in such a way that driving power comes mechanically from the crankshaft. The other alternative is to use a turbocharger system. A turbocharger system is not mechanically connected to the engine. The power to drive the compressor will come from exhaust gases. And the general development for high-performance engines, I like to look a little bit on BMW's M series, which started up very successfully in the 1980s, 1990s with fairly high revving naturally aspirated engines with multiple throttle plates, port throttling. And when BMW decided to go for turbochargers also for spark ignited engines, that happened when DI, direct injection, became available for spark ignited engines, and of course also variable cam timing. Then BMW and some other manufacturers decided to change from high revving naturally aspirated engines to turbocharged engines, and some actually selected to go for superchargers. So I would say that high performance engines have turned in the direction of more charged engine now and what it looks like into the future. Just a small equation as a teaser to start up this course. I call this the air equation. And as you know, if you have followed the other courses, air is the most important thing in order to create high performance in an engine. Fuel is of course the root cause for all power, but since it's no problem to get fuel into the engine, it's the air which is the challenge. And this is of course true to say if the combustion system is working in a good way and the mechanical integrity of the engine is in place. I have divided the air equation into 3 different contributors. It's the naturally aspirated contribution, we have the compressor contribution, and the charged air cooler, the CAC contribution. Starting with the naturally aspirated contribution. We have swept volume, we have an engine speed, we have a volumetric efficiency, the delivery ratio, and we have an air density available in the ambient condition. It could be at sea level or it could be at altitude where the density drops a little bit. The 120 is there for a reason. We like to input engine speed in RPM, revolutions per minute, and we have a 4-stroke engine which inhales every second revolution. So what we can do if we just have a naturally aspirated engine to control the air mass rate is engine speed, swept volume, and the volumetric efficiency. Taking the step to charge the engine, we add a compressor. The purpose with the compressor is not to increase the pressure. The pressure is a way to obtain a higher density. For most compressors, when you raise the pressure, unfortunately, you also raise the temperature. And according to the gas law, if the temperature is increasing, that will lower the density improvement because of the pressure raise. And to mimic that in the compressor contribution, here is the compressor efficiency. The better compressor efficiency we have available, the less temperature increase will happen over the compressor. But also a compressor efficiency of 100% will yield some temperature increase over the compressor. And in order to regain that density potential, we add a charger cooler which cool the compressor air. Just to give you an indication, a compressor with an efficiency of about 70%, which is rather good, working at a pressure ratio of 2, that means the compressor is doubling the pressure. The temperature increase over the compressor is about 100 degrees Celsius. So if the starting temperature from the ambient is 20 degrees, what will leave the compressor is an air temperature of 120 degrees. So also on a pressure ratio of 2.0, it's a good investment to use a charger cooler. Charger coolers could be of air-to-air type or air-to-water type. And they are expensive. They also take some room in the general installation. And as a rule of thumb, I normally say that if the pressure ratio is below 1.5, it's allowed to jump the charger cooler. Else, please keep it. And please keep it also lower pressure ratio because it really helps. Next step would be to look on all the components making up the system of a charged engine, so you know in what order of appearance you could expect to find the components. The ambient would be here at number 1. The first thing which happens is that we have a compressor which increases the pressure from station 1 to station 2. If you have a charger cooler, we have a station 3, and here there is cooled, but hopefully at almost the same pressure leaving the compressor. This would be the inlet plenum or manifold of the engine combustion system. We go to the red side, which is the exhaust side, and exhaust gases are pushed out. And if it's a turbocharger, the compressor is driven by the turbine. The exhaust gases passes the turbine, leaves power through an expansion, and expands out to the atmosphere again. Using a turbocharger, most likely we have a wastegate to control the boost pressure. If the compressor is mechanically driven from the crankcase, we have this one and no turbine and no wastegate. The first type of compressor I like to show you is the supercharger. A supercharger is always mechanically driven from the crankshaft. There are 2 types of superchargers. The first one I like to present for you is a displacement machine. It's in a way similar to a reciprocating piston engine. It has a certain swept volume, but in these cases the compressors are rotating the displacement device. There are 2 main types used today. The most common will be the Rhodes blower. One of the manufacturers for Rhodes blowers is Eaton, but there are others as well. GMC, for instance, doing larger superchargers for V8 engines. The other displacement compressor is called a screw compressor. They are similar in the way they build boost pressure. They are volumetric machines with a certain displacement, and matching the displacement of the compressor with the gearing to the crank forces air from the compressor, the air mass rate or volumetric rate, to be larger than the engine can swallow. And doing so, the pressure between the compressor and the engine will increase and we will have a boost pressure. This type of boost pressure buildup is called isochoric compression. It's not very efficient. And in the case of the screw compressor, they have a technology which includes internal compression. So the screw compressor have a higher efficiency, and the efficiency is also still pretty high when we increase the boost pressure. For the Roots machine, the peak efficiency is at a rather low compressor pressure ratio, around 1.5, as could be seen here in the small compressor map for the Roots blower. In the same way as an internal combustion engine have some level of volumetric efficiency, this is also true for both the Roots blower and the screw compressor. This is a dimensionless diagram showing how the characteristic of volumetric efficiency looks like. The screw compressor have a pretty constant volumetric efficiency down to a certain rotor speed, and then it drops off pretty quick. On the other hand, the volumetric efficiency for the screw compressor is pressure ratio independent. Going to the Roots machine, it has significantly better volumetric efficiency compared to the screw at lower compressor pressure ratios. At lower compressor rotor speeds. But on the other hand, the higher pressure ratio we have on the Roots machine, the more volumetric efficiency it loses. And the more you lose volumetric efficiency in the displacement compressor, the more boost you will drop and lose on lower engine speed. Another thing which is important to keep in mind for mechanical driven compressors, superchargers, is that they consume more power than you can expect. At the lowest pressure ratios, around 1.5, about 10% of the engine power needs to be spent to drive the compressor. If we jump up the compressor pressure ratio to 3, that's a very high pressure ratio, then that figure jumps up from 10% to 25%. So all in all, when it comes to superchargers or displacement type, we have a lot of points which is in the direction of mechanical driven displacement superchargers are best used at lower pressure ratios. But the supercharger can also be a dynamic compressor, centrifugal compressor, and then the compressor type is the same as for the turbocharger. The physics behind pressure buildup in a dynamic compressor is very different. We don't have a displacement. We have a blade, a wheel full of blades, which is rotating at a very, very high speed, increasing the speed of the air going through the compressor. The speed can be transmitted to static pressure by diffusion, and this is how a dynamic compressor is building up boost. This also means two things, that the pressure buildup will be very rotor speed dependent, which is not the case with a displacement compressor. If you have a mechanical drive to a dynamic compressor, this means that the boost pressure will increase very rapidly with engine speed. So at low engine speed, a radial supercharger will not produce so much boost. But it will act more or less like a slingshot, being very, very quick when the engine speed is going up. A compressor map for a radial compressor could look like this. This is in the application of a turbocharger where the drive for the compressor is not coming in mechanically, but by means of a turbine. We have flow on the horizontal axle, we have pressure ratio on the vertical axle. There is a limitation to the left for a dynamic compressor. It cannot operate here when the combination of flow and pressure ratio is just not suitable for the compressor. The boundary line here is called surge line. There is another flow limitation on the other side of the compressor map called the choke line. So the compressor could only be utilized in this part. The contour plots we have here is for different efficiencies, and in the middle, of course, the compressor is operating at the best. The curves going down like this is curves for constant compressor speed, indicating what rotor speed is needed in order to obtain a certain pressure ratio. The turbine looks surprisingly similar to a compressor, but flow in the turbine comes the other way, so it comes in here and goes out in the middle. The turbine is operating with hot exhaust gases, so both the turbine housing and the wheels are made of steel instead of aluminium, which is the case on the compressor side. In order to extract power from the exhaust gases are expanded in two steps in the turbine. The first step happens here in the volute, the stator, and the second expansion is happening in the wheels. And a turbine map looks a bit different compared to a compressor map. A compressor map have both efficiencies and the flow curves and lines in the same map, but the turbine have the swallow capacity represented in one part of the map, and the efficiencies are separated. To make things even more complicated, the pressure ratio is on the horizontal axle and the corrected mass rates are on the vertical axle. Why manufacturers and suppliers of turbochargers have selected this way, I don't know. Seems to be a little bit of a tradition. Okay, mechanically a turbine is rather complicated to achieve, but gas dynamic wise and thermodynamic wise, the turbine is actually easier to produce because a turbine is operating in a pressure gradient which drops. It's called negative pressure gradient, and it's easier to be able to achieve high efficiencies in such a regime compared to the compressor. Key parameters for a turbine is the A upon R ratio for the turbine or the area of the turbine housing. That in combination with the trim of the turbine wheel defines what swallow capacity you can expect. A complete turbine map is a little bit rare to find, while compressor maps are easier to find from the suppliers. The best and most refined turbine maps, like this one from Garrett, has also corrected speed resolved efficiency curves and swallow capacity curves. In my source list, I have several nice sources, books, which give you detailed information about compressor housing, compressor wheels, turbine to some extent. Nice pictures, much better than mine. But on the system level, how the compressor and turbine works together it's a little bit thinner in the background material. But one thing which I would like to add in this course, which might be a little bit of news to you, is how the pressure ratio over the turbine depends on the pressure ratio over the compressor. Pressure ratio compressor is called PRC, and pressure ratio turbine, which is on the vertical axle, is called PRT. The relationship between the pressure ratios can be obtained by doing a rather simple power equilibrium over the turbocharger. So assuming that the compressor is absorbing all the turbine power, taking the efficiencies into account. What you can find out then is that the pressure ratio over the turbine will drop always when compressor efficiency, turbine efficiency, and mechanical efficiency is going up. The same could be said if the wastegate mass rate taken away from the turbine could be kept low, which happens if you combine a rather big swallow capacity turbine with a compressor. That will also be in favor for keeping the exhaust pressure down. The third thing is exhaust temperature. So the higher exhaust temperature you could provide the turbine, the less work, the less pressure ratio is needed to be taken out from the exhaust mass rate. So therefore the pressure ratio of the turbine will drop for a certain constant compressor pressure ratio. This pressure balance might not be so important for low pressure turbocharger applications, but the more extreme engine you are turbocharging in terms of high boost pressure, and also if you select to choose very sharp camming, then the engine will be much more sensitive to the pressure ratio. So very good to pay attention to this. Connecting the turbine to a multi-cylinder four-stroke engine could be done in a lot of different ways. What I like to mention in this subject is the difference between a true pulse turbocharger system and a constant pressure turbocharger system. There are also some in-between solution which I call semi-pulse turbocharger system. If we start with a true pulse turbocharger system, the best number of cylinders you could link to one single turbine will be the inline 3-cylinder engine. It could also be an inline 6-cylinder engine with 2 turbochargers. That will be the same thing. V6 and Boxer 6-cylinder engines, the same. Because a 3-cylinder group, as stated in the multi-cylinder course, only have one cylinder's exhaust valves open simultaneously, there will be no interference between the cylinders, so you could have a clean pressure buildup between each gas exchanging cylinder and the turbine nozzle, building up huge internal pressures between the turbine and the engine. That will give a lot of turbine power available during the blow down period of the engine, which is a little bit free of charge, because in this part of the exhaust cycle it doesn't cost any pump work taken from the crank. And later in the exhaust phase, when the piston have reached bottom dead center and are on its way up, most of the exhaust gases have already passed the turbine. And this is one important reason why the efficiency of a pulse turbocharger system is high, and why you also get very good response from a pulse turbocharger system on a spark ignited engine when the starting condition is a low load. 4-cylinder engines are frequently turbocharged, and we all know that that works pretty good. but there will be interaction between the cylinders, so it's not possible to talk about the completely pure pulse turbocharger system, more maybe in the terms of semi-pulse turbocharger system. If we increase the volume between the turbine and the engine, we slowly move into constant pressure turbocharging system. This can happen on highly tuned engines with long exhaust primary pipes to be able to cope with very sharp cams. And they are actually introducing so much volume between the engine and the turbine, so they become a kind of constant pressure turbocharger system. Expect less response system. The most extreme systems I could come to think of is with cars with so-called remote turbocharger systems, where of installation reasons and thermal reasons, the turbocharger is placed somewhere at the rear of the car, having maybe 2-3 meters of exhaust pipes. Works absolutely, but the response and the matching is another thing. This constant pressure turbocharger and the pulse turbocharger system will have some different aspects of the matching, which I will try to cover on the next slide. Sometimes it's possible to achieve a special type of turbine efficiency curve, and it's called the U upon CS curve. Big U stands for the circumferential speed of the turbine wheel, and CS would be the speed where the gas beam hits the turbine wheel. Optimum turbine efficiency occurs at a ratio between U and CS close to 0.7. In a constant pressure turbocharger system, it's possible to have most of the operating points in the turbine map hitting the best possible efficiency point. So obviously a constant pressure system with all the drawbacks already described could more easily obtain the best possible turbine efficiency. For a pulse turbocharger system where the pressure ratio is going up and down, also the U upon CS will move around a lot. So instead of being here at the peak point, the U upon CS behavior will be very much up and down. So the average turbine efficiency might drop a little bit. What can be done, if transient performance allows, is to try to combine the compressor wheel with a rather big diameter turbine wheel. That will speed up the compressor a little bit, and doing so we will increase the speed of U and move this red area a little bit closer to the peak efficiency. As you can see, this course became also very long. I'm sorry for that. And this is the main reason for me saving some of the goodies regarding charging technology for internal combustion engines. I'm planning to make an advanced course where we look on multiple turbocharging system, both parallel and serial, depending on the goal with the charging system, and also the great opportunities we have combining supercharging with turbocharging. There are also different ways of utilizing turbochargers. One is to do supercooling. It's actually possible to cool the combustion air well below ambient conditions. And there are also opportunities to have mechanical or electrical links between the turbocharger and the crank to do something called turbo compounding, which could have some benefits. But that will happen a little bit later. Thank you for your kind attention and take care.